Good morning to one and all. In today's lecture, we'll discuss about the DPCM, that is Differential Pulse Code Modulation. Now here in DPCM, the modulating signal MT such as your voice or video signals are sampled at T is equals to NTS at the Nyquist rate of Fs is greater than twice of Fm, slightly higher than Fs, that is greater than twice of Fm, and we get the sampled version, that is your MNTS. So after the sampling with the Nyquist rate, that is your Fs greater than twice of Fm, there is an introduction of high degree of correlation between the adjacent samples. Now this is due to the signal does not change too rapidly from one sample to the next. So this result in the difference between the adjacent samples has an average power smaller than average power of the signal itself. Now, as coming on to the standard pulse code modulation, we use quantization as well as encoding. So, for the coded signal with redundant information symbol not absolutely essential for the transmission but generated in encoding process. So, to remove the reduced redundant information before encoding, this more efficient PCM is compared to your standard PCM. So for this we use a prediction process that is known as your differential quantization scheme. Now coming on to the DPCM transmitter. Here the transmitter consists of comparator, quantizer, prediction filter, adder and encoder. So initially your message signal modulating signal MT is applied to the comparator, that is the discrete version of MT. That is your, so here we have the prediction of MNTS, that is your MCAP and TS. So here the comparator compares the sampled version and the prediction sampled version. So after the comparison, the prediction error is generated at the output, that is denoted by ENTS. So we can say ENTS is equals to MNTS minus MCAP NTS, that is the prediction version of your sampled version. So here the sampled version didn't get the quantized, only the prediction error get quantized. So we get the at the output EQ NTS. And in the feedback path, prediction filter is used. So at the feedback path, we are using a prediction filter is used, and it is used to generate the prediction MCAP NTS and quantized version of MQ NTS. So here we get MQ NTS is equals to your MCAP NTS plus EQ NTS. Now for the simplified tape delay filter with T is equals to n number of delays as shown in the figure, here the quantized signal MQNTS is delayed up to T past sample value with corresponding weighted values denoted by W1, W2 up to WP. Here we are using an adder, that is a linear combination of the past sample values of MQ NTS, where P is your prediction value and that is known as your MCAP NTS. Now in the DPCM, at the receiver side, DPCM data sequence is transmitted via channel and the received by the differential pulse code modulation at the receiver. This differential DPCM consists of decoder, prediction filter, low pass filter. From the designing point of view, the prediction filter is at the transmitter side is same as the receiver side. So now we will discuss the differential pulse code modulation in brief by the mathematical equation. Now here the quantizer output can be expressed as EQNTS is equals to ENTS plus your QNTS, where your QNTS is the quantization error. So at the DPCM transmitter side, we get MQNTS is equals to your MKNTS plus EQNTS. At the prediction filter, your one input is your MKNTS and the second one is your QNTS. That is the quantized version of MTS. Now MQNTS is equals to, in place of EQNTS we can put ENTS plus QNTS. So now putting into the equation we get MCAP-NTS is plus ENTS plus QNTS. Now we get three terms over here. These first two terms represents your M and TS. Now if we note a point over here that your MNTS is not directly quantized, but the prediction error, that is ENTS, is getting quantized. That results in the perfect prediction. And the average power of prediction error, that is your ENTS, should be less than the average power of the sampled MNTS to produce the quantized error QNTS with the small average power. Now we can see in DPCM receiver, it consists of your decoder, prediction filter and the low pass filter. Here the prediction filter is same as that of the transmitter side. Here we get MQNTS is equals to your MKTS plus EQNTS, that was same in the transmitter side. Now here we can see that at the transmitter and the receiver we have same MQNTS and your MCAP-NTS. So this provide your noise-free environment. Now coming on to the special case, DPCM includes delta modulation except two important. The first one is in differential modulation, the one bit that or your two level quantizer is used. In differential pulse code modulation, prediction filter is replaced by a single delay element that is called as your zero prediction order. So by this we can say that your delta modulation is a one bit version of differential pulse code modulation. Here we can say that we note one more point, that DPCM, that is your differential pulse code modulation, like delta modulation, suffers slope overload distortion because the prediction filter is unable to track the fast changes in the input signal. Second, when the pulse code modulation and differential pulse code modulation are getting influenced by a quantization noise. So this was all about your DPCM. Thank you.